stage is yours. Thank you.
Thank you very much for the introduction, and I would like to thank the organizers for this wonderful opportunity to present our work at this very nice meeting. So I'll be talking today about imaging band topology in general and specifically in magic angle graphene. Our collaborators are the group of Dima Ifetov, which recently moved from ICFO to LMU. In particular, Peter and Georgia, and our team at Weizmann, which includes Samir, Indranil, Mati, Aviram, Yuri, and Alex Meltzer. Our theory colleagues and friends, Jiwan, Keshav, Binghai, Adi, and Eresberg, and the HBN crystals come from NIMS. So let me introduce you our experimental technique, which is SQUID-on-tip. We pull a quartz tube to a sharp pipette down to several tens of nanometers in diameter. And then we do a three-step deposition on one side, on the other, and at the apex, one of these superconductors, which gives rise to a very small squid that resides on the apex of a sharp needle, and therefore ideally suited for scanning probe microscopy. This is how it looks in SEM. You see one lead here. This is in particular a squid made of indium. One lead here, the other here, and you can see the hole at the apex. We can make these devices as small as 40 nanometers. They operate in magnetic field of up to 5 Tesla, in particular molybdenum. They have very good magnetic field sensitivity of down to 10 nanotesla per square root hertz, which translates into an excellent spin sensitivity. Namely, if you ask yourself, if I put some spins here, how many spins I can detect? And the answer is 0.3 Bohr magneton per square root hertz. Namely, we have sensitivity to image the magnetic field of a single electron spin. In addition, they're extremely sensitive thermometers because essentially critical current is temperature dependent. With a sensitivity of below a microkelvin per square root hertz at low temperatures. In order to scan close to the surface without crashing, we attach this SQUID-on-tip to a quartz tuning fork and monitor the resonance frequency of the tuning fork for force sensing, which allows us to scan a few tens of nanometers above the surface. So here are a few examples of magnetic imaging. These are vortices in a superconducting film. This is about 5 micron size image. And as we apply current, we exert Lorentz force on the vortices. They move to the right until we reach critical current. And then they penetrate from one side and move at huge velocities of tens of kilometers per second, forming these beautiful structures. This is a single vortex, which we wiggle back and forth by an applied AC current. That's why the vortex looks like a dipole. And in addition, we apply a DC current and exert a Lorentz force, or tilt the entire potential. And you can see as the vortex jumps from one potential well to another potential well, we can explore the full landscape, pinning landscape of a superconductor. These are ferromagnetic domains, domain walls in a ferromagnetic film. And you see the dynamics of the domain as we imply in-plane magnetic field. This is a quantum anomalous Hall state in a magnetically doped topological insulator. In the quantum anomalous Hall state, you expect the magnetism to be, you want it to be ferromagnetic, you want the entire sample to be in one magnetic state, but what we find actually that these materials behave as superpower magnets. Essentially, tiny islands of few tens of nanometer flip their orientation independently as we increase magnetic field. A similar behavior occurs at oxide interfaces. Again, nanoscale islands flip their orientation, but in this case, they're magnetized in plane. And that's why each event looks like a dipole. So each island flips its orientation from, let's say, x to minus x as we increase in-plane magnetic field. We can also, so all this was magnetic imaging, but we can actually image currents. So these are equilibrium currents that flow in graphene in a quantum Hall state. And in the quantum Hall state, we expect edge states to carry edge currents, the skipping orbits. And here you can see like 3 Landau levels, and each Landau level carries a current, which we call topological current. These are the usual edge states current that we expect to see. But actually, each Landau level carries, it turns out, carries a pair of counter-propagating currents. One downstream, the topological one, and next to it there's a current that flows in the opposite direction, which we call non-topological. Again, these are equilibrium currents that flow in a system with no externally applied current. So this is the first time actually equilibrium currents are being able to image in a quantum Hall state. This is a similar behavior now in magic angle graphene, in twisted bilayer graphene. What you see here in color, these are Landau levels. The red regions are compressible regions, and the dark blue are incompressible. And you see that Landau levels, rather than following along the edge of the sample, they're all over the place. And this is a 3D tomography sort of imaging of these Landau levels. This is 2 spatial coordinates, and this is the filling factor or the voltage that we apply to the backgate, namely how many carriers we have in our system. If the sample will be homogeneous and clean, the Landau levels should form just horizontal planes, parallel planes. Again, red are incompressible regions and the dark blue are compressible regions. But instead, you see that the Landau levels form very complicated manifolds. And this is because of twist angle disorder. So from these manifolds, we can actually extract the local twist angle of graphene with 1 millidegree precision with a spatial resolution of about 100 nanometers. So the typical or the standard twist magic angle is 1.1 degree, and you can see here variations from 105 to 1.18 degrees of local twist angle. This is forming this quite complicated landscape. And in addition, there are quite a lot of regions, this blue, that actually show no Landau physics, no magic angle physics at all. Either they are highly disordered or their twist angle is completely out of range. This morning, Anya mentioned hydrodynamics, which became in recent years, there's a lot of interest and there's strong evidence for hydrodynamic electron flow or viscous flow. So we have looked at this so we fabricated samples in this configuration of a strip. We've attached the 2 chambers, and the length scale is about a micron here. And we do this experiment in a gold film, and we drive current, and we do imaging of the current through the biosavar. So this is the Y component, the vertical component of the current. You see that most of the current flows in the central strip. And some of it goes into the chambers. This is the JX component. You see that the red means that the current flows to the right. You see that the current penetrates into the chamber and then exits. So the streamlines look like this. And if you do just simple ohmic simulations, this is what you find in excellent agreement with experiments. So this is just a regular ohmic flow. But now we repeat the same experiment in tungsten ditelluride flakes. And these are van der Waals flakes that we exfoliate into a few tens of nanometers thickness, and repeat the same experiment. So you see that the JY flows similar to what we had, but JX looks very strange. It's red, namely the current wants to penetrate into the chamber, but here it's white, it's blocked, it cannot enter, and instead there's a current flowing in the opposite direction, blue here. So actually the streamlines, most of the current flows in the center, but it cannot penetrate the chambers because of vortices that are induced in the chambers. And this is a numerical simulation of hydrodynamic flow in this case. And you see that the streamlines here, so in an ohmic flow, all the streamlines have to start from source and end at drain. That's what Ohm's law requires. But here you find that you have streamlines that close upon themselves without reaching source or drain. This is not allowed in ohmic behavior, and this is the first time vortices are observed in an electron fluid. So as I said, there was quite a lot of work on hydrodynamics, but the most obvious and intuitive let's say, the demonstration of hydrodynamics is vortices. So this is, as I mentioned, finally we can see vortices in an electron fluid. Let me show you a few examples of thermal imaging. So as I said, we have extreme high sensitivity, and we can do thermal imaging and study dissipation. So we have a sample like this. This is our graphene. We can bias it with a backgate, and we can also apply potential to the tip and change the local chemical potential under the tip. So this is our graphene sample, and we drive current from here to here. And this is a thermal map. And what we observe, surprisingly, is huge amount of rings all over the edges. And you can also see 3 rings here in the middle. And if I show you a high-resolution movie of the central part, you see these 3 rings expanding. The scale here is 300 nanometers, and the temperature scale is 40 microkelvin. We're at 4 Kelvin, so we can measure the local temperature with 6 digits after the decimal point. And all the interesting stuff is, of course, in the last digits. So these 3 rings, what you have to think is that in the center of each of this ring, you have a single atomic defect, and the incoming electrons undergo inelastic scattering and emit a phonon and a Cooler electron. This phonon propagates through graphene, through HBN, through helium exchange gas, helium atoms, that eventually hit our tip, and that's how we measure the local temperature. And the graphene is so clean that actually, in this field of view, there are about 100 million carbon atoms. And graphene is so clean that electrons have no way of losing their excess energy unless they bump into the single atomic defects. So in the bulk, they're extremely rare, and of course there are lots of them along the edges where you have all the dangling bonds and the add atoms and so on. So the only way for dissipation or for coupling between electrons and phonons are actually through these atomic defects. We can also study dissipation in a quantum Hall state. So essentially we repeat similar experiment at 1 Tesla magnetic field. And in the quantum Hall state, if you are in a plateau, dissipation is not allowed to occur in the sample. All the dissipation has to occur at the contacts. But what's surprisingly see that there is huge dissipation along the entire edges of the sample, and this comes from edge reconstruction. Essentially, there's edge accumulation, and instead of having the usual edge states and Landau levels that go up near the edge, actually you have extra edge modes propagating in the opposite direction, which allows you backscattering and dissipation. It's a tiny dissipation, so your RXX may be 1 or 2 ohms that you usually don't pay attention to, but actually this causes huge dissipation in the bulk that we can image locally. Moreover, we can even simultaneously measure the dissipation. This is the temperature scale, similar to what you have here, and what we call work, essentially the backscattering. So by measuring the resistance of the sample as a function of tip position and implying local potential to the tip, we can modify the local backscattering. And backscattering is an elastic process. It doesn't involve dissipation, doesn't emit phonons. Phonons are emitted somewhere else when the electron hits an atomic defect. So we can image these 2 processes simultaneously and understand very well where the tunneling occurs and where the dissipation occurs. So now let me move to the main topic of today, and this is topology. So topology is a fundamental concept in mathematics describing geometric properties of objects, and in particular, for example, the number of holes in an object. In recent years, we have realized that topology has an enormous effect on condensed matter physics, forming exotic states of matter, plenty of them. But still, topology is a rather abstract concept. I would like to pose the following question. Can we visualize somehow or image locally the topology? This doesn't sound as a meaningful question because we think of topology as a global description of your system, a global property, and in particular Chern number as a global topological invariant. Okay, for example, here the Chern number is the number of holes. So the meaning of local topology is not clear. But so let's take one step back and think what is the source of topology, and this is the Berry-curvature. The integral of Berry-curvature over the Fermi surface of a full band must be an integer, and this is the Chern number. For example, in graphene, the Berry-curvature comes from the Dirac point, and if you open a gap at the Dirac point due to breaking some symmetry, your Berry-curvature spreads over the bottom of the band such that the total Berry phase at the bottom of the band in the K valley is pi, and in the K prime valley is minus pi. So in contrast to Chern number, which is defined only for a full band, the Berry-curvature is defined for any chemical potential. So we can actually ask ourselves an even more general or perhaps a more fundamental question whether Berry-curvature can be visualized somehow or imaged locally. But again, this question doesn't make much sense because Berry-curvature is defined in the K space, and there's no clear meaning of Berry-curvature in real space. But we have to remember that Berry-curvature acts as magnetic field in the K space, and it creates orbital magnetization very similar to a regular magnetic field. So now, but orbital magnetization now is a measurable quantity, and it is well defined in real space. So actually, imaging orbital magnetization provides an answer to these fundamental questions. The problem is that the orbital magnetization is usually too weak in order to be imaged, and so far it hasn't been visualized. So now we have an opportunity for the first time actually to image the local orbital magnetization and to try to address these fundamental questions. So the orbital magnetization that arises due to Berry-curvature has quite strong analogy to orbital magnetization in the quantum Hall effect. So in the quantum Hall effect, we have two contributions to orbital magnetization. In the bulk, in the compressible states, the electrons form closed orbits, and these orbits give rise to a diamagnetic moment. But in addition, we have edge states along which the electrons flow in these so-called skipping orbits due to presence of in-plane electric field. This is the confining potential. And these edge states actually give rise to chiral currents that flow in the opposite direction and create paramagnetic moment. So we have this competition between diamagnetic and paramagnetic currents in the quantum Hall effect. This is one of the images that I've shown you in the beginning where we can actually image these currents. Very similarly, Berry-curvature has two contributions to orbital magnetization. One is the self-rotation of the wave packet, which we call M self-rotation, which is analogous to these closed orbits of electrons in the quantum Hall state. And the other is the so-called anomalous velocity, anomalous drift velocity, which arises in presence of in-plane electric field, which is analogous to these edge states. So the self-rotation magnetization is dominant in the metallic state, in the compressible regions, and the drift velocity is dominant in the insulating state, let's say in the Chern insulator. And by this analogy, we expect the self-rotation and the Chern magnetization generally to be of opposite sign. They don't have to be, but we expect them generally to be of opposite sign. So now let's move to our experiment. So this is a magic angle graphene device from, as I mentioned, Dima Fetov's group. And if you do transport at 300 millikelvin, and this is a magic angle of 108 degree in this device, you see all the beauty of the magic angle graphene. To those of you who are familiar with this, you see these Landau levels, Landau fans. You see Chern insulators, these more prominent lines. You see correlated insulators, these large resistance gaps. You see superconductivity. In this region, actually, the resistance goes to 0. And on top of it, you see magnetism. So for example, in this sample, there is magnetism here near filling factor 1. So 4, it means, filling factor 1, it means that you have 1 electron per moiré unit cell. And you have room for 4 electrons because of spin and Welle degeneracy per moiré unit cell before you fill the flat bands. And if you focus on this region, and actually magnetism has been observed in magic angle graphene by a number of groups, and usually it appears near a filling factor of 3. In this particular sample, it appears near a filling factor 1. So here, if you do transport and you increase and decrease your magnetic field, you see a hysteresis. So this is RXY, and you see a large pronounced hysteresis. In some devices, this anomalous Hall effect or anomalous resistance reaches quantized value. Then you are in the quantum anomalous Hall state. Here you reach, let's say, 5 kilo, which is a fraction of quantization, but still significant one. And towards the end of the talk, we will understand why we cannot reach full quantization in this case. You can also sweep back and forth the filling factor, and you see hysteresis also as a function of filling factor. So this is very intuitive that this is a magnetization. This is a little less intuitive, but we will understand it later on. So these are transports. So now we do this experiment and study the local magnetization. So this is how the setup goes. This is our SQUID. This is our sample. We're at 300 millikelvin. We apply a very small magnetic field of 50 millitesla, essentially a zero field, and we ground the sample. So there are no currents flowing in the sample, no externally applied currents that flow in the sample. We apply a backgate voltage, DC voltage, in order to change the carrier concentration in the device. And we will be focusing near filling factor 1, where in transport we saw magnetism. And on top of it, we apply a small AC backgate, in this case 0.08 electrons per moiré unit cell. And what we measure is the local magnetic field, AC magnetic field, in response to this AC modulation. Namely, what we measure is by how much the local magnetic field changes due to adding and removing 0.08 electron per moiré unit cell. And this is what we see. So this is the local magnetic field in nanotesla. So the signal is extremely weak as a function of position. And you see regions that have positive magnetic field and negative this AC magnetic field. We can reconstruct from this local magnetic field, we can actually reconstruct the magnetization, assuming that it's out of plane, that generates this local magnetic field. And the units now are in Bohr magneton per electron. And you see that the numbers are on the order of 20 Bohr magneton per electron, which means that it cannot be a spin magnetism, as Eugene discussed this morning. Actually yesterday, right? Or it was today? Ooh, whoa. Okay, so I have to really speed up. So this is the magnetism that we measure at a filling factor of 1 after we initialize the system at high carrier density and then reach this filling factor. And now we do the same experiment by initializing the system at low carrier density and then bringing to the same. And this is the difference between the two. And you see that in large parts of the sample, the magnetization is completely reversible, doesn't care about the history. But in other parts of the sample, it is strongly hysteretic. And if you look carefully, essentially this image looks exactly like this one, and like this one, just with opposite sign. So it means that this entire region has flipped its magnetization as a whole, despite the fact that some regions have positive magnetization and some regions have negative magnetization. This is how it looks in 3D. So again, this is sweeping the filling factor up, sweeping the filling factor down, and this is the difference between the two. And you see that orbital magnetization creates complicated patterns and occasionally sharp first-order transitions. So in order to understand the origin of this, we do some very simple band structure calculations, assuming full degeneracy lifting, at least Welle. So we ignore spin, And due to interactions, we assume that there is degeneracy lifting between k and k prime values. So this is the calculated band structure in the flat band. And this is the calculated Berry curvature, which has a maximum at the gamma point at the top of the band. And from this, one can also calculate straightforwardly the orbital magnetization. And you see that it's on the order of 30 Bohr magnetons per electron, very similar to what we observe experimentally. So this is k resolved, but we have to integrate over all k's, or average over all k's. So this is the calculated magnetization, differential magnetization that we should measure as a function of filling factor. This is the self-rotation magnetization, which increases gradually and becomes maximum at the top of the band. And then in the gap region, since there are no states, there should be no self-rotation magnetization. The other part is the Chern magnetization, which is essentially zero in the metallic state, and then becomes large and negative in the gap. And it is dictated by the Chern number. So this is what we expect theoretically, and this is what we measure in reality, which is very different. But if we look more carefully, we can actually make some sense of it. And if we look at this patch, we see that we start from, we expect, so we are here, we expect to become sharply red and then sharply blue. And this is what we see here as a function of filling factor. So now we know that we've reached the gap. And in the gap, we are dictated by the Chern number. So I'll skip a few slides. Sorry about that. So actually, just to make the long story short, when we reach this point, the magnetization, either we can start filling the next band, in which case the total magnetization will become negative and highly unfavorable energetically, or we can recondense all the electrons from K valley at this first order transition into the K prime valley like this, and then the entire magnetization will flip through a first order transition. So again, I have to skip all this. And so when we are in the gap region, the local orbital magnetization is simply given by the Chern number. So we can actually, red means that locally we have a Chern number of +1, and blue means that locally we have a Chern number of -1. And this is, so now we have a tool to actually determine the local topology, and it's completely general. So essentially we're measuring local sigma xy without driving any external current. It just tells us whether the currents locally circulate clockwise or anti-clockwise. Again, with no externally applied current, just the orbital magnetization. And from this, we can extract the map, the full map of the local Chern number, and this is how it looks. So we find patches on the order of micron size that have either positive or negative Chern number, and regions which have zero Chern number. So actually, instead of being a global topological invariant, now the Chern number becomes a local property, which is very different from what we think in general about topology. And there are a lot of consequences of that. One of them is that these are now, we will have chiral edge states along these patches. So let me just summarize. So we provide the first observation of equilibrium orbital magnetization, which allows us to study local topology and Berry curvature. We find that actually the Chern number forms a mosaic with positive and negative Chern numbers. And this is essentially a new type of disorder that one has to take into account. We find that there is a first order transition of recondensation of electrons from one valley to another. And as I mentioned, the edge states are chiral. They should carry current. We can actually image this current directly. And this is shown in this movie as we change the filling factor. So these are actually topological currents that flow in the system that we have to be aware of when we do transport measurements and other studies. Thank you very much for your attention.
Thank you very much. Thank you very much for this impressive talk and results. So I'm sure there are many questions.
Hi, thank you for your great talk. I have a question. So in the beginning of the talk, you said that these graphene samples are very clean and that you have ballistic transport. And at the end of the talk, you say, okay, there is some locally varying band structure. How do those two phenomena correlate? I mean, where is this inhomogeneity coming from?
Okay, so magic angle graphene is much more prone for disorder as compared to, let's say, to monolayer graphene. And the main source there are two sources of disorder. One is the local twist angle, as I've shown in the beginning, changes, and it changes the band structure. So the band structure is directly related to how flat the bands are, directly related to the angle. So if you have angle variations, all your band structure moves, and this creates these crazy Landau levels and so on. The other is, in this particular case, the reason that you have different Chern numbers is the substrate potential. Unfortunately, I didn't have time to dwell on it. This is how your local A or B sublattice is aligned with boron or nitrogen atoms in the HBN. So if your A sublattice sits mainly on the boron, you will have a Chern number of +1, and if your A sublattice sits mainly on nitrogen, you will have a local Chern number -1. And this is another type of disorder that we usually don't think about.
Thanks.
Okay. Only one short question and answer in the back. Then we have to move on.
Okay, thank you. I have a question about one plot that you showed in which you have a hysteresis in the magnetic field as well as in the filling factor.
Right.
It's not always the case that you observe a hysteresis in the filling when you scan the filling factor. Is that something that is general for the case of scanning this magnetism that gives you the hysteresis in the magnetic field, or not, and why?
Okay. So our understanding is that if you open a gap, if you have a Chern gap, you should have orbital magnetization and quantum anomalous Hall state. So if your entire sample, in order to observe quantum anomalous Hall state, you need one of the Chern numbers to propagate from one edge to another. Here, as you can see, there is no percolation. That's why you see hysteresis, but it's not quantized. Now, whether it is hysteretic or not, as I've shown you in one of the slides, large parts of the sample have the same physics but show no hysteresis, where the others do show hysteresis. Hysteresis comes from pinning of the domain walls, not from the physics itself. It's sort of a second, like in a ferromagnet, right? You can have a soft ferromagnet, you can have a hard ferromagnet. So this is a ferromagnet, orbital ferromagnet. Whether there is hysteresis or not, it has to do with pinning of the domains, which is another level of complication, but it's not fundamental one.
Thank you very much.
Sure.
So let's thank Eli once more. And we move on to the next presentation.